Unit 10 would cover solutions and different types of reactions, including acid-base precipitation reaction and some redox reaction. We start with the solution. What happens when a solute dissolves? If it's an ionic compound, it would change to ions, and the attractive forces that between solutes and solvent exist. They can separate the ionic compounds. This, as an example, separated to ions. We did talk about this in Unit 9 as well, but I was going to talk about solution in this unit to make sure that I can also talk about electrolytes. Okay. So what's happening, sodium and chloride, they attract each other strongly as in a solid sodium chloride. When you add to the water molecule, since it's polar, from plus side or positively charged part of the molecule is going to attract the chloride ion, and from the negatively charged side of the water molecule is going to attract the sodium ion, and so sodium and chloride is going to separate. Now, in the molecule, then we are going to have chloride separated from the sodium ion. So we have ions like negatively charged and positively charged ions. So the whole solution is going to basically contain plus and minus charges. Ions, they can transport electrons, and solutions that they do have solutions that contain ions, they are known as electrolytes. Electrolytes, it's basically applies to solution that can transfer electricity. So if we have a solution of sodium chloride, for the reason that we talked about, solubility, or when it dissolves, is going to give us Na plus and Cl minus. We have these ions in the solution, and it can transport electron from one pole to the other pole. So basically, ions can bring the electrons from one to the other pole, and solution is known as electrolyte. This test is done with the conductometer, which is shown in this picture as a simple device. The light bulb is going to only light up if electrons are transferred from one pole to another pole. Now, if they're not transferred, then the light is not going to turn on. Now, if you see it like a dim light, then the solution is going to classify as weak electrolyte. So we do have a strong electrolyte and weak electrolytes. Okay. So ionic compounds, they are electrolytes because they dissociate when they dissolve in water, and then non-electrolytes, they are going to stay as the whole molecule, and since it stays as a whole molecule, it does not generate ions. As a result, it's going to be non-electrolyte, or they don't transport electrons from one pole to the other pole. At the molecular level, this is what you can see. Ions of sodium and chloride, they are separated, but the sugar molecule or molecular compound, they're going to maintain their molecular structure. No ions are produced. Some samples of electrolytes. like acids, strong acids, they dissociate 100%. So they are classified as strong electrolyte because they dissociate 100% and they have high population of plus and minus charges or ions. When it comes to weak electrolytes, they dissociate partially, or a small percentage of it dissociates. That means the number of ions that is generated from a weak electrolyte is going to be limited. When you have limited number of ions, then electrons are going to be transported, but limited amount, and the electrolyte is going to be more specifically classified as weak electrolyte. So in the weak electrolyte, the light bulb is going to be dimmed light. It would turn on, but very low. The number of ions is lower. And if you look at the equation, you see this double arrow. A double arrow means that the reaction is reversible and is not 100% dissociation. When ionic compound dissolves and you see a single arrow, that means that 100% dissociation. A double arrow means that it's reversible or partial dissociation, and partial dissociation indicates weak electrolyte. Examples of weak electrolyte, it could be like weak acids, weak base, and some ionic compounds that they don't dissolve completely in water. Non-electrolyte would be insoluble ionic compounds and molecular compounds because they don't generate ion. Okay. It's showing strong electrolyte, weak electrolyte, and non-electrolyte. In the weak electrolyte, we have dimmed light as it shows here. Okay, so you have the dimmed light for the weak electrolyte. Okay, some ionic compounds are soluble in water, others are insoluble, and then we do have some that they are partially soluble. Solubility can change with the temperature, so it depends on temperature and it depends on the nature of the compound. How do you know compound is soluble or not? It's not easy to predict it, so it's better to do some experiments and determine if the compound is soluble or not. Well, other people have done these experiments multiple times and they came up with the rules. So these rules are actually the result of many experiments. This table shows the solubility rule for the compounds, that they are generally soluble. So if you need to be able to read this table, what it says, any compound that contains group 1A, like lithium, sodium, potassium, or ammonium ion, is going to be soluble without any exceptions. So if you see sodium chloride, we know that it's soluble because it contains sodium, because sodium is in this first rule with no exceptions. If you have potassium bromide, it would be soluble because potassium is in this rule with no exceptions, soluble with no exceptions. Ammonium, so if you have NH4 chloride, ammonium nitrate is going to be soluble because anything that contains ammonium is going to be soluble. Second rule with no exceptions, if there's anything that contains acetate ion or nitrate ion would be soluble. Those are clear. Now, what about the ones with the exceptions? If it says chloride, bromide, and iodide are soluble with exceptions to this, that means if you see lead chloride, it's insoluble because The lead chloride is an exception. So chlorides are soluble except if they are lead chloride, mercury chloride, or silver chloride. Sulfates are soluble unless you have silver, calcium, strontium, barium, lead. That means if you have sodium sulfate, it's going to be soluble, but if you have silver sulfate, is going to be insoluble. If it's insoluble, S indicator is used, and if it's soluble, AQ indicator would use, or subscript would be used. Compounds that are generally insoluble, those are the compounds that you have them in this list. Hydroxides are usually insoluble, except if you have them like lithium, sodium, potassium, or ammonium, or calcium, strontium, barium. These are also known as strong bases. They are known also as bases. Metal hydroxide, they are strong bases. Sulfides are insoluble. And what does it mean? Again, that if you have iron sulfide, it's going to be insoluble. But if you have sodium sulfide, it's going to be AQ, soluble. That's what it means. So if you have any of these ions combined with the sulfide, it's going to be soluble, but anything other than this small list, it would be insoluble. Carbonate and phosphate, they're insoluble unless you have one of these four ions. The solubility is used in the precipitation reaction to predict if there is a product or not. What is a precipitation reaction? If you have two clear liquid, you mix it, a precipitate forms. That means insoluble compound forms. There is some misconception that students think like a block of solids should form. That's not the case. If the solution would turn cloudy, and if it turns cloudy, that means insoluble compound has formed. So in the reaction of potassium iodide with lead nitrate, just going to practice, if you just follow along, potassium iodide is soluble because we said anything that contains potassium is going to be soluble. Lead nitrate is soluble because we said anything that nitrate contains nitrate is going to be soluble. Lead iodide is insoluble because we said iodides are soluble except if it's lead iodide, mercury, or silver iodide. So lead iodide is insoluble. Potassium nitrate is soluble because any compound contains nitrate is soluble. Any compound containing potassium is soluble. So it is soluble compound. So there is a reaction. The evidence for the reaction is formation of precipitate or formation of this solid compound. When you mix two aqueous solution, means that solutions that are soluble compounds in water, and as on the product side, you have also two soluble compounds. This means there's no reaction because you have mixture of four ions, like you have potassium ion, iodide ion, sodium ion, and chloride ion. On the product side, you also have potassium ion, iodide ion, and sodium ion, and chloride ion. So you start with mixture of four ions, you end up with mixture of four ions. That means there's no reaction. The reaction takes place if there is a change in composition or new compound is forming. So how would you write a precipitation reaction? First of all, you're going to to find the ions that you have on the reactant side. I already included this in another unit, but just as a review to make sure that it is covered here also. You want to, for precipitation reaction, you're going to exchange the ions. And when you exchange the cations or anions, then you write proper formula with considering the charges of each ion, and then check the solubility table to see if you have an insoluble compound or not. If there's insoluble compound, you would write S, and if it's soluble, you indicate with AQ. If there is no precipitate, if all the products are soluble, there would be no reaction. And this is, and then you have to balance equation. You just have to be careful when you're writing the product, you write in proper format. So this is an example of a precipitation reaction. So you have potassium carbonate and nickel chloride. They are soluble because based on solubility table, these two compounds are soluble. Now we have potassium ion, just following the in, out rule that I used before. Nickel would go to with carbonate, and potassium would go to with chloride, and you write the new product, the new compounds that are forming. Potassium is 1+ charge, chloride is a 1-. So your final product or the formula for the product is going to be KCl, regardless that you have 2 potassium and 2 Cl, but the proper formula is going to be KCl. You have to use proper formula for the product. And then nickel is a 2+, and 2+, and carbonate is 2-, so it's going to be NiCO3. Now, potassium chloride, it's soluble, is AQ, and based on the solubility table, NiCO3 is insoluble, so it's going to be S. So we know there is a reaction, and NiCO3 is the precipitate. Now, the next step would be to balance this equation. We have 2 potassium, so we have to use 2 for KCl, and that would give you 2 potassium and 2 chloride. We do have 2 chloride here and 1 nickel, 1 carbonate. So by adding coefficient 2 for KCl, you balance the equation as well. So this is a precipitation reaction. It's balanced, and the evidence of the reaction is formation of nickel carbonate. And balanced equation. Now, to write the molecular ionic equation from the molecular equation, this is the molecular equation. Your next step would be to write complete ionic equation. To write complete ionic equation, you need to break down anything that is an AQ designator. With AQ designator, we have 2 potassium ion, carbonate ion, and nickel 2+ plus 2 chloride ion. On the product side, we have 2 potassium ion, 2 chloride ion, because it's potassium chloride is a potassium chloride plus and minus. The coefficient 2 is just to balance the equation. Then when it comes to nickel carbonate, because it's solid, you're not allowed to separate it. So you would write as it is. So this is the complete ionic equation. Now, if you cancel the spectator ions, which is the 2 potassium from both sides of the equation, they are identical, and 2 nickel is going to what is left, it's known as the net ionic equation. So from complete ionic equation, we can cancel the spectator ions, and we go to net ionic equation. The net ionic equation is going to be nickel plus carbonate and that yields to nickel carbonate, and this is the net ionic equation. The net ionic equation is usually responsible for the evidence of the reaction, and we see that precipitate is forming from that. Okay, next type of reaction is acid-base type reaction. In acid-base or neutralization reaction, you start with and you add an acid to a base or a base to an acid in order to neutralize it. So nitric acid with calcium hydroxide, which is a base, it gives you salt and water. Okay. If the salt is soluble salt, then these would count as spectator ions, and the only thing that is not canceling is the water, because if you have solid, you cannot, for solid, liquid, or gas, or molecular compound, you cannot break down to ions. If you have solid, liquid, or gas on the product side, would stay. So if the salt is soluble salt, then the net ionic equation for acid-base reaction is going to be H plus OH minus yields water. So acid plus base, it gives salt and water. H plus sometimes is also known as H3O, O plus. Okay? And the reason for H3O plus is that H is a small ion and it attaches itself to water molecule to be stable. Because it's small, it cannot carry the plus charge. Base dissociates and they give hydroxide ion, and in acid-base reaction, H from acid with base, OH from the base is going to make water. Cation from the base with anion from the acid is going to make the salt. So you end up with salt and water. Some common acids, the perchloric acid, nitric acid, sulfuric acid, hydrochloric acid, that these are strong acids. So it's good to know if you have strong or weak acid, because we learned before that weak acid is a weak electrolyte and a strong acid is a strong electrolyte. Hydrobromic acid is strong. Hydroiodic acid also is strong acid. So if you want to add to the list of strong acids, HBr and HI, these are also strong acid. Okay, strong acid. Group 1A metals of group 1A and 2A hydroxide, these are strong bases. Then you do have like ammonia, ammonium hydroxide, or organic bases that they contain nitrogen, like aniline. They are weak bases. Okay. In acid-base reaction, water would form plus the salt, as we said. So if you want to write the ionic and molecular equation for the nitric acid and calcium hydroxide, you have two strong acids that they both are going to dissociate to their ions. And then you can treat this as like a double displacement reaction or precipitation reaction similar to that, or double displacement in general. Then you would say in, out, or hydrogen would go with the hydroxide, and then the metal with non-metal or anion is going to give the salt. So we have the salt, and since the salt is soluble, the net ionic equation is going to be H plus and OH minus, that yields to H2O. The equation must be balanced, and in order to balance the equation, you can just balance it one element at a time, or to make sure that your reaction contains same number of hydrogens on both sides or same number of oxygen on both sides. It's just balancing equation. If you change the aqueous compounds to ions, but we cannot change the water. As I said, is liquid, is not aqueous, is liquid. There's a difference between liquid. Liquid is like pure water. Aqueous means that something has dissolved in water. So pure water does not generate ions or is not considered ionic compound. Okay. From the acid-base reaction, we can use titration. Titration is a method to determine concentration of unknown solution, unknown acid or base. If you have a standard, which is acid or base with a known concentration. And in the for the titration, you would start with, let's say you have an acid in a flask, you would put the base in a burette, and you must have an indicator in the flask, or you must use an indicator or pH meter. For 1045, use indicator. You would use the general chemistry too. There's, you can use the pH meter for different purposes. But for titration, you pick the proper indicator, which is an indicator that would show color change at the neutralization point of this acid and base. So you're going to slowly add base until you see color change. When you see color change, that is known as the end point of reaction. So be careful with that. Make sure that you have the definition for endpoint and equivalent separately. So endpoint of the reaction is when the indicator changes color, but okay, endpoint of the reaction when you see color change. So equivalence point is when the number of moles of acid equals the number of moles of base. So that would be the equivalence point. When indicator changes color, that's known as the endpoint of reaction. As you add the base to the acid, the hydroxide from the base with H plus from the acid is going to combine, changes to water. When all hydroxide or enough hydroxide is added to neutralize all the hydrogens or protons that you have, H pluses in the solution, and then you have a neutral compound. Titration can be used to determine concentration. So if we use this example or follow along this example, it says titration of 10 milliliter of HCl solution of unknown concentration. So we know that it's HCl, and we know we're using 10 milliliter, but since we don't have concentration, that would be our unknown. Requires, when you are doing like a aqueous solution or reactions or precipitation, or when you are using two aqueous solution, The one that has both concentration and the volume, that would be your given. The one that is missing concentration, that would be unknown. Or if it's missing the volume, if you have the concentration but you don't have the volume, that would be unknown. So both concentration and volume needs to be known in order to consider that compound as a given. So in this example, HCl is your unknown because we don't have the concentration, but the base, the sodium hydroxide that you are using, because you have both concentration and the volume, is known as the given. So given is sodium hydroxide. Looking for is HCl. We do have the volume for HCl, but we need the concentration for HCl. First step, start with balance equation, because the balance equation is going to tell us at the equivalence point how many moles of the base is needed to neutralize a mole of the acid. Okay, so if you use this definition, molarity times liter of solution, that gives you the moles of solute. The map that we used in the past, for the given, you want to find the moles of the given. So if you find the moles of NaOH, and in order to find the moles of NaOH, that would be the molarity. So moles of NaOH equals molarity, which is 0.1, and that is mole per liter, times volume of NaOH in liters, because we want to cancel the liters, and that would be 0.01254 liter of NaOH. This would give me the number of moles of the NaOH. Whatever you find here as the moles of NaOH is going to be equal to moles of HCl, because we have the based on balance equation, 1 mole of HCl is going to react with 1 mole of NaOH. So that would be equal to number of moles of HCl. Now, if we have the moles of HCl, which is going to be the moles of the solute, and we have the liters, which is the 10 milliliter divided by 1,000, if we can find the molarity. So that's how you would approach. First of all, identify what's given, what's looking for. Second, make sure you have the balance equation. And when you have the balance equation, you find the mole ratio and find the number of moles of the given. Then you would find the number of moles of looking for using the ratio from balance equation, which in this case was a 1-to-1 ratio. Then you find when you have the moles of the HCl, then molarity would be mole divided by liter. So you have the you would get the number of moles for HCl divided by 0.01, and that gives you molarity for HCl. Oh, that's moles. And then you want to divide that by the divide the moles by 0.01 HCl to get the molarity for HCl. Reactions that involve gas, then you can also calculate the number of moles of gas from the reaction. So if you treat the same, so for that, we just want to look at some of the reactions that they do involve gas, like a sulfide plus acid would give you product of gas. Then sulfite, that's a sulfide plus acid. Sulfite plus the acid would give you sulfurous acid, and sulfurous acid is unstable. It would decompose to H2O liquid and SO2 gas. So sulfide and sulfides, those are the examples. Carbonate and bicarbonate plus acid, it gives carbonic acid, and carbonic acid, because it's unstable, it would decompose to CO2 and H2O. The carbonic acid, which is the H2CO3, is a combination of these two. But since it's unstable, it would decompose and it gives gas molecules. So metal sulfide plus the acid, or metal carbonate or bicarbonate plus the acid, it gives you products of gas, sulfite and bisulfite, and ammonium. Ammonia would give the gas of ammonia. We can use the balance equation to find number of moles of gas is being produced. So when you have the in this case you have sodium carbonate, and the other table we had metal carbonate plus acid, it will generate gas. So metal carbonate plus the nitric acid is going to be double displacement reaction, or kind of acid-base reaction. So we have sodium going with nitrate and hydrogen with the carbonate. We get H2CO3. H2CO3 is unstable, and it will generate CO2 plus H2O gas. And usually you don't write this intermediate. You can write directly the final product, which is the H2O and CO2. You want to make sure your reaction is always balanced. In order to balance in this reaction, you must use 2 moles of sodium nitrate. With the 2 moles of sodium nitrate, you need the 2 moles of HNO3. You only need 1 carbonate, so you don't have to change this, but you use 2 HNO3 and 2 NaNO3. Okay, so this is like reactions that involves gas, another type of reaction. So we looked at precipitation reaction, we looked at the acid-base reaction, and reaction involving gas. Another type of reaction is oxidation reduction reaction. In oxidation reduction type reaction, the one element or one is being oxidized and another element being reduced. We have different type of oxidation reduction reactions, or with different type of reactions that can be classified as oxidation reduction reaction, like a combination of with oxygen or combustion type reaction. In a when you have element combining with oxygen, it can be classified as the oxidation reduction. I'm trying to get to the pen. Stop working for me. Sorry for the pause. Okay. In oxidation reduction type reactions, lose of electron, gain of electron, it's the, okay, lose of electron is for something being oxidized, gain of electron is for definition for element that is being reduced. So combustion reactions, anything combining with oxygen, again, is a combustion reaction, and that classifies as oxidation reduction type reaction. Reactions of metals with non-metals, because metals like to lose electron and non-metals gain electron, and that's the story with the reaction of metals with non-metals. Metal would lose and change to cation, non-metal would gain electron, change to anion, then electrostatic attraction between the two is going to form the formula unit or the ionic compound. In oxidation reduction reaction, one is being oxidized. That would be the element that is losing electron, and the element gaining electron is being reduced. So what happens in oxidation? Oxidation number of the element that being oxidized is going to also increase. So if oxidation number for sodium in free state or solid phase is 0, and after losing electron is going to change to +1. So oxidation is taking place. Chloride is gaining electron. Oxidation number for chloride in free state, the way it's gas, is 0, and it can, after gaining electron, is going to be -1. So oxidation number is going to be lowered. So Leo, lose of electron, is oxidation, lose electron oxidation, and gain electron reduction. In order to see what is being oxidized or reduced, you can find the oxidation number or oxidation state, which is not charged but is a sign number, and you can find the oxidation number and track it if it's being increased or decreased in order to determine if the element is being oxidized or reduced. There are some rules that can determine the oxidation number, help you to determine the oxidation number. Elements in free state, oxidation number is 0, just like the example that we had for sodium in solid phase, and then we have chlorine in gas phase is going to be 0. And ions, monoatomic ions, the oxidation number equals to the charge of the ion. The sum of the oxidation number for a compound is going to be equal to 0. So if you have the oxidation number for one and not the other, you can set up equation and determine the oxidation number. Sum of the oxidation number for ions or elements in a polyatomic ion equals to the charge of the ion. Group 1 metals, they have oxidation number of +1 always. Group 2 would be 2+, and hydrogen is going to be +1, except in hydride. So hydrogen is going to be +1. Oxygen would be always -2, except if it's with the peroxide, which is going to be -1. And group 7A, -1, that's the oxidation state. But in general, unless group 7 is facing with another group 7 element, oxidation number is allowed from group number to minus of the group number. But fluoride would always be, fluorine would be -1 in a compound, hydrogen in a compound would be +1, and oxygen would be -2. Group 6A often is -2, but that's not actually a solid rule. For group 5A is going to be from anywhere from +5 to -5 is allowed. Okay. Okay. Assigning oxidation number is just a practice to follow along with this practice. Element in free state. So Br2 is going to be 0. A monoatomic ion, oxidation number would be equal to the charge. So that was the rule. Oxidation number for group 1A is a +1. Oxidation number for fluorine is -1. So we know that for fluorine. CO2 oxidation number for oxygen is -2. So 2 times -2 is a -4. Since the total is going to be 0, carbon must be +4. So for that, you can just set up an equation. You could say X, which is the oxidation number for carbon. Or for C, plus 2 times -2 equals 0. So X plus -4 equals to 0. X minus 4 is 0, and X would be +4. You can find the oxidation number for carbon that way. Sulfate, oxygen is -2 because it's not peroxide. So the total needs to be equal to the charge of the ion. So X, we are going to put the oxidation number for sulfur as X, plus 4 times -2 equals -2. That's the charge of the ion. This was the rule number 5. And X minus 8 equals -2. You bring the -8 to the other side of the equation, it's going to be +8. -2 plus 8 is going to be +6. So you set up this equation. Sodium is always +1. And if sodium is +1, 2 times +1 equals 2 times X. So oxygen must be -1, or you could say in peroxide, that you can use that as the next rule. Oxidation number of oxygen in peroxide is always -1. Okay. If the oxidation number is increased, oxidation has taken place. If oxidation number is decreased, reduction has taken place. So if you know how to determine oxidation number, then you can predict if it's being oxidized or reduced. We also have two other definitions. One is reducing agent and oxidizing agent. Oxidizing agent or reducing agent is basically helping something else to be oxidized or reduced. A reducing agent is helping something else to be reduced. How something is being reduced is by gain of electron. So if element wants to be reducing agent, must provide electron to another element to be reduced. So it must lose electron. So if it's losing electron, is going to be oxidized itself. So in this example, sodium is being oxidized because it's losing electron. And when it is oxidized, it's going to provide electron for chlorine to be reduced. So what is being oxidized is acting as reducing agent. What is being reduced, okay, Cl2 is being reduced. That means it's gaining electron, it's pulling away electron from something else. And if it's pulling an electron from something else, it's going to make the other or something else as oxidized, is pulling electron. So what is being reduced is acting as oxidizing agent. Here's an example to determine what is being oxidized, reduced, and what is oxidation, what is being defined as reducing agent or oxidizing agent. First, we want to find out which one is being oxidized. Let's take a closer look at this. Is hydrogen being oxidized or reduced? In order to find out a hydrogen being oxidized or reduced, you find the oxidation number of hydrogen on the reactant side. Then you find the oxidation number of hydrogen on the product side. There is no change. So it's neither. Okay. Sulfur, oxidation number is -2 on the reactant side. And how do we know it's the -2? Because it's combined with 2 hydrogen and the total must be 0. So we have 2 minus for sulfur on the reactant side. On the product side is 0. If it's going from -2 or 2 minus to 0, oxidation number has increased. If the oxidation number has increased, that means it's being oxidized. If it's being oxidized, that means it's acting as reducing agent. Okay, so sulfur is being reducing agent. Oxygen is -2 in every compound on the product and reactant side, so neither oxidized or reduced. We look at the nitrogen here, X plus 3 times -2 equals -1, and X minus 6 equals -1. So X equals +5. That's how you determine oxidation number nitrogen to be +5. And on the reactant side. On the product side, it's kind of easier because we know oxygen is -2, so nitrogen must be +2. If it's going from +5 to -5, it's been lowered by 3, so it's being reduced. If nitrogen is being reduced, it's acting as oxidizing agent. Manganese from +4 going to +2, so it's being reduced, and if it's being reduced, it's going to be oxidizing agent. But when it comes to Br from -1 going to 0, the oxidation number has increased, so it's being oxidized. If it's being oxidized, that acts as reducing agent. No change for hydrogen, no change for oxygen. So we only look for the ones that there is a change in oxidation number. Combustion reaction is another type of combustion reaction, is a oxidation reduction reaction. In a combustion reaction, element is going to gain oxygen. So gaining oxygen also, every element from the compound gains oxygen. So gaining oxygen is another definition for oxidation. So if element being oxidized because it's gaining oxygen, oxygen is being reduced. So we have the oxygen being reduced, carbon being oxidized, carbon, and then hydrogen. So we go with the definition of for each one gaining oxygen, so being oxidized. In a combustion reaction, carbon would yield to CO2 if it's complete combustion. Hydrogen would yield H2O, sulfur SO2, and nitrogen from a compound after combustion, it can give either NO or NO2. Okay, this example of combustion reaction, we have a combustion of C3H7OH. When it says combustion, it's going to be combining with the O2, and carbon with O2 is going to give CO2, plus hydrogen is going to give H2O. Now, what happens with the oxygen? I mean, oxygen with oxygen is going to give oxygen, so there is really no need to write it. When you're writing the equation for combustion of organic molecules or hydrocarbons, if there's only carbon, oxygen, and hydrogen, you would get CO2 and H2O. For carbon, hydrogen, you would get CO2 and H2O. But if there is a sulfur, it would give SO2. If you have a nitrogen, it can give NO2 or NO, depends on the amount of oxygen provided. In this case, when you have the equation, you should balance it. For combustion reaction, you should always balance the carbon from left to right, hydrogen from left to right, and oxygen from right to left. So we have 3 carbon, it gives 3 carbon dioxide. We have 8 hydrogen, is a 7 plus 1, that gives 4 water molecule. So we have 3 times 2, that's 6 oxygen, plus 4 oxygen, that's 10 oxygen. The 10 oxygen, we need 5 O2, and that's how you balance the equation. For CH3 NH2, in this case, plus O2, you would get carbon would generate CO2, hydrogen would change to H2O, and nitrogen would change to NO2. Then you are going to balance the equation based on the number of carbon on each side, 1 on each side. So that would remain 1 nitrogen on each side. That's good. Number of hydrogens, we have how many hydrogens do we have? And we have CH3NH2, that's 5 hydrogens. Is going to give us CH3. That would give us like 2.5 H2O. H2O. So we have 2 oxygen and 2 oxygens, that's 4 oxygens. 4 oxygen plus 2.5, that is 6.5. We see what gives us different answer from the two hydrogens, 3 hydrogens, that's 5 hydrogens. Okay, this product, either the product is not, or I'm not thinking well. This cannot be a balanced equation. We have 3 oxygens as 2, 4, and 6. That gives 3 oxygens. Carbon is 1. Nitrogen is 1, but hydrogens are not balanced. It was a solved problem, but this is not correct. It is not correct, and we need to correct this one. It could be like there is a different, also a product of NO here. I'm not sure, but it doesn't match. But based on this is not correct. We have 2.5 here. It's going to change the number of oxygens as well. So we have 5, 2, and 2. 2, 6, 8. It's not going to work. Okay, I'm going to have to stop here, solve this problem, and put a new video for you. It's